Okay, thank you. I hope you can hear me. So thank you first for the invitation. Unfortunately, I couldn't be on site, which is really a shame because, okay, we have really a lot of teaching period now, a lot of teachings, but okay, hopefully next time we'll be in the same good place. So I'm going to talk about mostly software things and about the design of for the design of different kind of circuit, digital, mixed signal, also quantum. I won't have time to talk about all the points, but I will make an overview with a few tools. Some of this work out of this software, Stanislas Ilin, Lukas Ivanikov, and Christian Verollet, so I won't show all of the work they did. So to place the context, if I can change the page, yes. Globally, we have now a fast development of quantum systems because of many, as you probably know, many projects started in different a lot of software to design systems which are not so intuitive, especially quantum ones. And this software are also for education in some. So a range of software have been developed, and all these quantum systems, in any case, they cannot be developed without being surrounded by a few enabling technologies, which include superconducting electronics, but there is also CMOS electronics, and of course all the tools to design computer-aided design software tools, CAD tools. And for the last decades, in fact, the advances on this design of complex circuits have been slowed because it takes a lot of time to design the circuit, especially when they are based on Josephson junction, where the physics is not so obvious. And there was a lack of user-friendly and performant tools. Though, of course, in each research lab, every researcher or PhD student has developed its own software to advance knowledge and to assist the design and make progress in the lab. But these software, they always stayed in some way, in some niche and quite intimate, and they have not been spread. So it is changing a bit now with GitHub and with Python. There is a lot of Python things available now, but still it's not yet totally at the level we would like to have. So I don't know why. Okay, yeah, I need to press here. So for the software development, of course, superconducting electronics is the most demanding for fabrication because there can be complex circuits, and then as a consequence, software tools need to be able to sustain these difficulties, this complexity. And quantum systems can be smaller. They have only a few qubits or a few hundreds qubits. So they are not so complex in terms of number of devices, but the calculations are necessary to find eigenstates and to find the dynamics of quantum systems is quite heavy. And in this case, it requires large computing powers and especially statistical analysis. So we all need to have a software for both quantum and superconducting electronics. So regarding superconductors, because quantum is not necessarily just based on semiconductor or solid-state devices, can be other kind of systems. But concerning superconductors, the first software which is necessary for the designer is a time domain simulator, basically, to see how logic circuit behave. And for quantum software, we need, of course, to solve Schrödinger equation as the first step, and then go to more complicated equations to take into account, in particular, dissipation with some master equation of Lindblad, for example. So, and on top of that, these circuits, whatever they are, qubits or superconducting electronics, they need microwave. Basically, they handle microwave most of the time. And there is a range of simulator tools, which is also necessary for passive microwave elements, like transmission line, resonators, couplers, filters. And all these tools are necessary to make the final circuit. I'll show you a few examples of what we did of user-friendly applications software, but they are not yet totally all embedded in the same suite, but it's going to happen little by little during the coming years, and some part is going to be finished as well by the end of this year. Superconducting passive transmission lines, there are really elements that are necessary for different kind of systems, mostly because for digital circuits, they are interconnects, and so they appear between logic gates and they need to be simulated correctly. And for example, for qubits, you also have transmission lines that are used as resonators often, and also one needs accurate models to know their behavior, to adapt, let's say, the environment of qubits. And their properties, like propagation velocity or characteristic impedance, strongly depend on the physical parameters of superconductors, especially around the gap energy where a lot of things are happening. So we developed a standalone tool that allows to calculate the properties and visualize the evolution of pulses along lines based on the Matisse-Bartin theory. And we have it as standalone, but we also will have it as a part of a larger suite. It's not yet finished, its second part, but the standalone already application works. So to illustrate why we need to have these accurate simulations, I just present SFQ pulse, theoretical SFQ pulse in case there is no capacitance. With two pulses, you see them in black, with our NIC of 1 millivolt and 0.5 millivolt, and you have in blue the spectrum. The frequency axis is in the top of the graph, and you can see that the spectrum in blue has some component, especially for the narrower pulses, which are above the gap frequency of niobium, which is about 700 gigahertz. You see there is some energy above the gap frequency. It means such a pulse, 1 picosecond pulse, has enough energy to break a few Cooper pairs, and it has an influence even if the line is superconducting and without losses. In fact, it has losses at high frequency, so there is dispersion. As just an example of the signal. So we developed this software to apply these signals to a PTL, a passive transmission line. If we calculate characteristic impedance and propagation velocity, you can see the variation of these two parameters around the gap frequency, clearly, which is very important. So which means the properties are modified. And so we developed this tool, which has a few menus. We can put SFQ pulse, but we can put also other kind of signals like solitons, Gaussian pulse, and a different sinusoidal signals, of course, and all kind of other things. I just show you the interface with SFQ pulse, where you can choose the dimension of the line. You can choose a physical parameter. It means London penetration depth on each superconductor for microstrip line. Dielectric constant of the insulator between the layers, the tangent delta, which is the losses of the insulator at high frequency, and of course some user parameters depending on what you want to do, at what temperature you want to use the system, and also with what frequency step you want. So you can choose for the pulse the period, the width, the position of the pulse versus the function of time. The software calculates at low frequency, for example, the characteristic impedance, as you can see, and the propagation velocity. And when you do a few simulations, you get this kind of curves. I show a few ones here. On the bottom right, you have the conductance, normalized conductance, imaginary and real part. It's a logarithmic scale on the y-axis. So you can see at the gap frequency, you have something happening. Basically, you have an inductance changing, and the resistance is getting high very fast. Basically, the real part of the complex conductivity is getting fast, and you can see the influence on pulses. When you take a pulse of 3 picosecond, which corresponds roughly to current density not far from 1 kiloamp, you see that there is not so much dispersion, but the pulse is slightly attenuated. At 1 picosecond, which corresponds to more aggressive technology, you have clearly a stronger attenuation because of what I told you before, and you see the effect of the dispersion with oscillation on the tail. And it's even worse when you have a pulse width of half a picosecond. To give 3 examples. If you check the attenuation of the SFQ pulse for a different distance, this simulation has been made by assuming it's not a superconductor. So I assumed it was normal metal with conductivity. Okay. So I'm coming back to this curve. So you can see the voltage, how the pulse voltage is attenuated over length, with a kind of a normal metal transmission line. And you can see that the attenuation is logarithmic as we expect. It's an exponential decrease of amplitude, but only for high lengths. Why we don't have this linear behavior, or rather exponential behavior at low lengths? It's because the size of the pulse is bigger than the one of the line, or of the order of magnitude of the one of the line. Then we are not in a propagation mode. We are rather in, I would say, a near field mode. That's why we have this difference. But if you make calculation with the superconducting lines, well, first you see it's better, the attenuation is lower, and we have this quite exponential behavior from 10 millimeter lengths, but before it's not, the amplitude is not decreasing exponentially, because again, we have a line which is not so long compared to the physical size of the pulse. So that's one example of what we can do with this software. I'll show you another software that we use to determine the properties of squids. So it's interesting when you design, for example, new digital cells. When you want to have this, you need to understand how the cells, the phases will arrange in a circuit to optimize the design. So we started to do that with the simple squids to see if we are able to calculate that. So it has been done through a static analysis. So the software looks like that. You can enter the parameter of the squid, the critical current, you can enter the inductances, and you can see the magnetic patterns, what is important for a squid, meaning the critical current versus external magnetic field. In red, you have the unstable solution, which are mathematical, but we can remove this. The application allows us to remove this unstable solution to keep the physical solutions. So it helps to know how to optimize the bias current, especially of these devices, for squid, but also for SFQ circuits for simple cells. We can also map the contour, what we call the contour, the loci of phases. It means the phases which correspond to solutions. So you have this red and black curves which correspond to, if I remember well, to flux quantization, and the other blue curve corresponds to the fact that the total current is the sum of the currents of the two junctions of the squids, because they are in parallel. So there is a relation between the two phases. But we can also do that for more complex circuits like biscuits, which are nice because they have been proposed by Korneff a few years ago. They are nice because they have a voltage flux relation, which is linear, much more linear. It's interesting, especially for analog to digital conversion. You can see this triangle to the right. So our software also allows to do that. We can calculate the contours. In this case, there are three junctions, right? You have a squid down with a junction junction A and B, and you have a third junction, which is C, which has been added to make it linear, more linear. And in this case, you can see the contours of these three phases in a 3D, which correspond to solutions of equations to respect flux quantization in all the loops, and also of course, the current imposed by the user. And we can also map the magnetic patterns. It can be in some cases quite complicated if you take random parameters, as you can see here on the down part. But if you find the right parameters, as shown in the paper of Korneff, we can simulate. We reproduce here for comparison with the software. We get these blue curves, and they correspond basically to the curves, the red curve in the right, taken from the paper of Korneff. So we have some good agreements, but there are still some. Here we have some unstable solutions which are plotted, but we can see the linearity at least. Another software that we use is for when we want to go with high frequencies in digital circuit or even analog circuit. We need to have microwave oscillators integrated in the circuit. It can be done with a train of pulses, but it can also be done in different ways with an overbiased junction, for example, very overbiased. So we can simulate when we apply whatever voltage waveform. We can simulate what will be the current. We can calculate all the properties of the junction due to tunneling, and we can get the AV curves. So this is also all this software I didn't mention. They all work on Windows and Mac and Mac OS, both systems. And so you can see here the IV curve, which is an input of this software. We can find the Kramers-Kronig transform due to causality, which is a blue curve. And from that, we can deduce IV curve in presence of microwave signals. Here, there were two signals, one at 200 gigahertz and another one at 400 gigahertz, an harmonic. And you can see the influence and you can see the quantum steps on the IV curve. So, which means the junction is receiving a signal at high frequency. And that's also something that we can incorporate in some circuits when we need to combine digital with analog signal. And I will finish with this slide. I don't know exactly if I respect the time. I was supposed to be nearly finished. There is a paper publication on that you can find on IEEE, Transaction of Applied Superconductivity. So I will not detail it here. It's called Join Us. It has been issued, but it's not yet totally ready. So this software allows to take netlist of a digital circuit, to make simulations, to add the noise, to make simulation of this digital circuit with the noise, to calculate the margin, the yield in particular, all the main features that we need to have when we design a digital circuit. And also we have the possibility to extract parameters through inductex to back annotate on the netlist. So all these manual things that we were doing before, now we can do them all integrated with the same software. Maybe later we will add a WRSpice, but it's not planned for the moment. We have other tools to add to join us, including the tools I showed you before. So we can also put PTL, passive transmission lines, as a cell, and they can be simulated directly. So that's about it for the presentation of the software. We have also some for quantum simulation of single photon, how to say, qubits interacting with single photon detectors, and also other than that. But there are several models that we can use when we simulate Josephson junctions. Not only this simple one with Cooper pairs, but also models with other or more complex models. Say we can do pi junction, phi junction with when the phase is any value between 0 and 2 pi. And also very soon we'll be able to have to simulate any kind of. So that's about it. I want to acknowledge Conrad Fourier, Joe Delport for the JOSIM simulation JOSIM simulator that we integrated in Jonas, and also Masoud Peram, who really supported us for all this during all this work. And we had several French-Ukrainian projects which helped us to do that. And the YARPA Super Tools program, which funded at least the people who work on that. Thank you.
Thank you for nice presentation. Can you hear me? No.
Maybe you can ask.
Okay. Can you hear me now? This nice talk. I would like. Can you? Your software.
Of course, well, you are talking with one junction only. We didn't do it in this program. Indeed, we were not looking for that. It's implemented. The Fraunhofer, well, the variation of critical current of Josephson junction is modified if you apply, for example, in Jonas, if you apply a magnetic field. But we cannot see at this stage, we cannot sweep, have interference, but we didn't put diffraction. And it's not so complicated to add diffraction. So I think it's a good idea. We could add it. So we can, it will help to see what's going on when we have a general circuit, yes, and especially with the larger junctions, it's interesting. The junction, I'm going to, this one you mean? This one, the black one? This one, the black. Yes, this is a measurement indeed. It's a 1 micrometer Josephson junction. It was about 10 kiloamp quasi-particle. So experimentally, what we did, we suppressed with diffraction, in fact, and we put the right magnetic field to suppress the Josephson current, Cooper pair currents, and then we just keep tunneling the quasi-particles. That's why. It was to compare with our measurements that we did that.
Okay.
But in fact, what I didn't talk about it, but we are developing, it's nearly finished. We are developing a model which can take into account everything, including in presence of microwave signals. It means Cooper pairs and quasi-particles in presence of microwave signals. It's quite more complicated. But it's going to be implemented in the coming months. Yes, I mean the code is ready. We need to put it in the rest of the.
About the software you mentioned. He's
yes.
On, right? No. So, do you mean usage of combined Ginzburg-Landau model and Bogolyov-Dijen model? Because basically you can extract, having the order parameter, you can establish the, Cooper pairs and quasi-particles. So what you are saying about is pretty much about implementation of Bogolyov-Dijen's model, right? For
theory, and we put all the equation coming from causality effects and with all the good physics in it for the normal, let's say normal, simple Josephson junction. But of course, we plan to have it for all kind of relation between phase and current. And so that means that we need to modify the, I would say, there are, how to say, it's a kernel, it's a frequency kernel of the system, meaning the spectrum, complex spectra of quasi-particles and Cooper pairs versus, of course, versus frequency, but the spectra of currents, of tunneling currents. In the general case, this is what we are implementing, that will work the same. The software will work the same.
Do you use quasi one-dimensional Bogoliubov-Dijen or 2 or 3-dimensional Bogoliubov-Dijen equation?
Yeah, it's a mesoscopic scale, I would say, right? We don't solve the order parameter. For example, we don't simulate order. Assume that we have some global behavior.